So, in our last lecture we had talked about the simulated annealing method of placement. Now, today we shall be looking at a number of other methods which also have been attempted to solve the placement problem. The first method we look at is something called simulated evaluation. Well, the way we present the method, this is also a version of the so called genetic algorithm. So, first let us try to understand what this general concept of genetic algorithm framework is and how the placement problem is mapped into this. Well, the concept of genetic algorithm is simple. Well, in a simulated annealing you start with one solution, but in genetic algorithm you start with a set of solutions. So, with respect to placement, there is a set of placement configurations to start with. So, you have a set of solutions which you call the population. There is the concept of a population which is a collective set of solutions. There is some kind of a cost function with respect to which you can evaluate the goodness of each of the members of the population. So, you can measure the goodness, which is sometimes called the fitness measure of the members of the population. This is also an iterative method like simulated annealing. There are three operations or processes which are carried out. These are called crossover, mutation and selection. So, let us try to define and understand what these three operations are. Well, the way we present these operations, it will be specific to the placement problem, but if you want to apply this to some other problem, you will just have to change the definitions, but otherwise the framework will remain the same. First, the crossover. Well, in order to explain the crossover operator, just I am explaining first one thing. Suppose you have a given population, okay. This is your given population which will comprise of several solutions. Now, when I apply the crossover operator, what I do is that I take any two solutions from the population, okay. I apply the crossover operator on this, I get two new solutions. This is the basic idea. I start with two solutions, apply crossover on them and get two new solutions, right. Okay. So, how this is done with respect to the placement problem? Suppose I have two solutions. One solution is, say, this is a placement solution, this. I choose a random cut point. So, in terms of x coordinate, I can choose randomly a cut point here, for the other solution also in the same place. Well, intuitively speaking, what I am trying to do is that I am trying to take the first half of solution 1 and the second half of solution 2, put them together to get the new solution. Most of the crossover operations for genetic algorithm implementations do it this way. But for this placement problem, if we simply do this, it can lead to a solution which is not correct, because a particular block may be repeated in both the halves or some of the blocks may be absent. So, you will have to make a small refinement to this basic idea. But I say some block may get repeated while some others may be deleted. So, one way to handle this situation is that, well, you take the first half of this solution, you try to put the second half of the second solution to this, but while trying to do this, so you take the first half of this and the second half of this, you may see that some block, say A, which is here, is also coming here. Naturally, some block which was here is missing. So, you try to find out that through a search and you replace this block A by the other one. Do this to get a feasible solution out here.
Which one to replace among these two A's is also
That is just a matter of implementing, how you implement it. See, the intuitive reason of the crossover operator is like this. See, I have a number of solutions available to me. So, I have computed the fitness of all. So, the two solutions I take for crossing over will be the two which are good in terms of their fitness values. This is what I always attempt to do. Now, if the two solutions are good and if I combine the first part of one good solution with the second part of another good solution, possibly I will be getting a better solution. I am trying to take the good features of two solutions and combining them, possibly I will be getting a better solution. This is again a random way of doing it, but I am using the fitness value of the solutions to select the good parents, you can say, to generate the good children. And also there is another parameter called the crossover rate. Well, we do not do this crossover blindly. Every time I take 2 and do a crossover, I take 2, then I compute a random number and check against a given probability value. If it is within the crossover rate, then we apply it, otherwise you simply copy it to the next generation. Given the population, we apply crossover to get the population of the next generation. So, we move from one generation to the next.
So
Yes.
For this crossover, you are selecting every two sets in the generation, or only
2 at a time.
two at a you have to do crossover with all of them.
Yeah, I'll just I'll basically come to this point. Whether we are taking all or not, I'll come to this point a little later. But we are taking 2 at a time.
Talking about this crossover rate, I did not get.
Crossover rate is that suppose I take 2 solutions and I am just about to do this crossover. Before doing this, I compute a probability, and means if my generated random number lies within that probability value, then I actually do the crossover, or else I simply copy them just as it is. Okay.
So do we perform inter-generation crossovers?
No, crossovers only within a generation. So, once generation I plus 1 is computed from generation I can be deleted. Okay. There is another operator called the mutation operator.
But sir,
Yes.
this probability crossover rate is like, what is the background of having this generating a random number? Right?
See, some of the parents are good, I do not want to disturb them, let them be present in the next generation also. Because if I always
But then why am I generating that random? I can have a cost associated with each parent, and if it is good, I just copy it.
yes, I'll basically come to that point. I will just come to the point shortly. The second operator is called a mutation operator. This basically makes some small random change to a solution. Take a solution, make some random change and put it in the next generation. So, the one common way of doing is you do a pairwise exchange of 2 blocks. Now, the frequency with which you carry out mutation again is determined by a mutation rate. Now, the mutation rate is a very small number, maybe it is 1% or 0.5%, typically like that. So, this mutation you carry out much less frequently as compared to crossover. Now, the purpose of mutation is that you try to make a random change and possibly go to a new solution. From there, possibly you will be getting some better solutions after you apply crossover again. This is the intuitive justification. Well, now coming to your question, the select operator actually selects the members for crossover. Now, from experience, what has been found is that suppose you have a generation out here, this is generation I. Generation I contains several solutions. So, you have to produce generation I plus 1. So, each of the solutions will be having an associated fitness function or a cost function. Well, experience shows that this algorithm works best if you do this. You select the first few best solutions, simply copy them, few best. So, the few best solutions simply get percolated to the next generation. Okay. Others will get generated through crossover. The way crossover is applied is that you select two solutions at random, well, not really at random, their chance of selecting is directly proportional to their fitness value. Higher the fitness, greater is the chance of their selection. So, using that kind of a randomized way, you select two solutions from this. Well, maybe you are selecting means one of those best, no problem, I can. You select two of these, you apply crossover or do not apply crossover depending on the crossover rate. Now, whatever is your decision, those two resultant solutions you simply copy here. You go on repeating this till the next generation is full. This process you repeat.
So number of members in GI will be equal to number of
Equal. Generation sizes are same, the population sizes will be the same. Now exactly what will be the size of the population, well, like how many iterations will carry out, these are all subject to experimentation. But this is the basic skeleton of the genetic algorithm. You have to represent a solution, but the solution representation is important here. It should be such that crossover operation can be applied very efficiently. Because for this placement problem, it is a little problematic. The way of cutting and checking and doing it, this is not very efficient. So, there are other algorithms where the solution representation and the way you do the crossover, it can be done very easily. Okay, fine. So, this is the essential idea behind genetic algorithm, and some people have also tried to apply this.
Is this used widely?
This is not used in commercial tools, but there have been a number of works which have been reported where placement was solved using genetic algorithm. The results obtained was good, but the time taken was not that good, means the time taken to arrive at the solutions were much higher as compared to simultaneity annealing. So, in practice people do not use genetic algorithm for placement.
It seems that genetic algorithm is better implemented if used with standard cell libraries. I mean, where you can easily be swapped.
Yeah, possibly yes, yes. If a standard cell library, the swapping and other things are very easy. Yeah, yes. General cell it will be very difficult. Yes. Now, one thing you understand that about 90% or even more than 90% of the design efforts that people give nowadays are towards standard cell only. All the chips you design today, there very rarely they will be a full custom kind of a design. Typically, you pick up cells from the library, you put them in standard cell arrays. Okay, you are right. Okay, next let us look at an interesting method, well, which was proposed. This method is interesting, but well, because of the computation complexity, this is applicable only to small placement problems. But let us look at this method, it is very interesting. See here, the method is based on an analogy. This analogy or a similarity between the placement problem and a problem of classical mechanics, a system of bodies which are connected by springs. See, in the placement problem, what is the thing? There are several blocks which are connected by wires. More the number of wires, more is the attractive force. So, the placement algorithm will try to bring them together. Similarly, if there is a spring, so as the blocks become further, or the weight, the springs may be stronger or lighter, depending on the strength of the string and their distance, the attractive force will be different. So, the attractive forces that two blocks experience and the attractive forces, well, this body of springs experience, they are very similar and they are guided by Hooke's law. More the distance, more will be the attractive force. Okay. So, it tries to use this analogy. Magnitude of the force is directly proportional to the distance between the blocks, and the objective is that you try to obtain a final configuration which is the equilibrium condition, where the net force exerted on each block is 0. That is the final configuration. So, if you can find out a placement which satisfies this, that is your best placement. Okay, so in terms of concept, it is very interesting. So, let us try to formulate this problem first. Okay. Say I have a cell I, this is my cell I. This cell is connected to several other cells. Let us call one of them J in general. So, a cell I which is connected to several other cells in terms of the netlist will experience a total force which will be defined as the weight of each link. This weight is Wij. This Wij can be just be the number of watts connecting block I and block J. Weight multiplied by their distance, Manhattan distance. This will be the weight between I and J. So, if I is connected to several other blocks like this, then it will be the sigma of it summed over all J's. This will be the total force exerted on block I by the other blocks in the surroundings. Now, the idea is that similar to a spring, if the block I or cell I was free to move, it will move in the direction of the force Fi until the resultant force on it is 0. This is what we are trying to do. We are trying to find the final location of block I such that both the x and y components of the force on it become 0. And this we iterate over all the blocks, so that all of them try to move to their 0 force target locations. Okay, let us see the calculation for block number I. With respect to block number I or cell number I, suppose xi0, yi0 represents the 0 force target location. Now, these two equations will follow. You see, block number I was here, block number j was here. Okay. This block number I has moved to its 0 force location, let us call it I0. Now, initially the force between I and j was Wij into xj. Now, since it has moved to a new location this, it will now be Wij into xj minus xi0.
Wij into xi0 in the new location.
No,
Wi0
this j has a coordinate of xj and yj. This new location of the block has a coordinate of xi0 and yi0. Now, since this has moved to this new 0 force location, I am equating the x components and y components separately. With respect to the x components, the difference between the x component between this j and this I0 is xj minus xi0. Similarly, y component is yj minus yi0. These two equations I am writing separately. One is the weight between these two multiplied by the difference in the x components, weight multiplied by the difference in y coordinates. These sigma over all j's will be separately 0. Okay, the x components and the y components of the force were separately equating to 0. Now,
So, but why have you taken Wij? You should have taken Wi0j.
well, I0 is the coordinate. Well, this is not really I0. I am saying that this I which was xi yi, this has moved to a coordinate xi0 yi0, which is the 0 force target location. But it is actually the same block I have written it as I0, but it is actually the same block I which has moved here.
So, weight is dependent on
Wij is the number of watts that connects block I with block j. That will remain same in the new location also. Now, in this equation, if you just move it here and there, you can easily solve for xi0 and yi0. This will be the final expressions. Sigma wij xj divide by sigma wij. Similarly, sigma wij yj divide by sigma wij. So, you can use these two expressions to find out the 0 force target location of a particular block, right. Fine. And of course, one thing you have to keep in mind explicitly you have to check that that means you are not leading to block overlap. Two or more cells should not be assigned to the same xi locations. This is something you have to check separately. Okay. Fine. Let us take a simple example to illustrate it. Suppose I have a problem like this, a simple inverter. These are the IO pins or IO pads, whatever you call. A is the input, F is the output, VDD is the power and ground. So, this gate has to be connected to these four things, right. Now, what I am assuming that I have a 3 by 3 grid. I am taking a small example just for the sake of illustration. I have a 3 by 3 grid. I am assuming that these 4 terminals or pads are located in the 4 extreme corners. So, here I have VDD, say, here I have F, here I have A, and here I have ground. Now, I can place this inverter in any one of the remaining 5 cells. Now, my objective is to find out the best location for this inverter in these cells, so that the force, so that it corresponds to its 0 force location. Now, what we assume is that some weights. So, let us assign some weights to these lines also. Well, these weights may be depending on the number of lines or depending on importance. Okay, so this I am just assigning arbitrarily. So, there is no justification behind these numbers. These are the numbers I am assigning, and these are the coordinates 0 0, 1 0, 1 0 2 0. This is again 0 0 on this side, 0 1, 0 2. Fine. Now, on this problem we can compute using the expression we have just shown before, this xi0 and yi0. We can simply compute the xi and yi expressions. Xi0, see xi0 I can calculate the weight multiplied by the, you can say the x VDD. Okay. Now, we assume that the gate is initially placed here in this location. This is your ij. From here I want to find out the 0 force location. So, initially the gate is placed here. So, in terms of the x coordinate, the weight of VDD multiplied by the difference in the, well, in the x coordinate. How much is the x coordinate difference? X coordinate difference is 0, 0 2 1, okay, 1 plus ground multiplied by difference between ground and this in terms of x coordinate is also 1 plus
So, but this possibility opposite direction.
so it is a distance, it is a distance, we are not talking of the sign really. Okay, 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 minus 1. VDD into minus 1, right? VDD into minus 1. 5 into 1 plus in terms of A will also be minus 1 plus F will be 1 divide by 5 plus 5 plus 3 plus 10. How much it comes to? Minus 5, minus 8, 7 by 23. Similarly, yi0 will be computed to something similar. See, this after xi0 and yi0 are computed, you will be getting some values. Now, you try to approximate them to the nearest integer and try to see that whether you can place it in that particular location. That will be the best place to put it in. So, basically this algorithm will work like this.
So, but it is not necessary if I place it to the nearest integer, that would give me some option.
No, see, this is the zero force location. You try to place it as close to that position as you can. That is the idea, because you cannot place in a fractional place. So it has to be aligned with the grid, because we are assuming some grid x y z x y. So this you are approximating it to the nearest grid point. You are trying to place it there. Okay. Fine. So this is the essential idea behind constructive placement. You have a problem, you try to take one of the blocks at a time and try to place it in the most desirable location. You can go on iterating. Now this force directed placement can also be used for some kind of constructive placement, like you are trying to build up a placement starting from scratch. Here I am assuming that a placement was already given, you are trying to improve upon it. This is iterative refinement. But as an alternative, you can also have a constructive placement mechanism, where starting from scratch you are going on building up the placement. How? You can see, you can basically start with the fixed blocks. You take one of the modules at a time, try to find out the zero force location, put it in, take the next one, put it in. In this way you build up it, and then you can iterate a few more times to improve upon the overall thing. So this force directed placement is used both for iterative refinement as also for constructive placement, both it has been used. But as you can see, since it involves quite a bit of computation to find the zero force location, so it is useful only for small designs, and for big designs often you will find that the xy coordinate you are computing, they will be mapping into the same grid location for multiple blocks. There will be overlaps. So for general designs, this method will have limited utility. But the method is interesting, but it has limited utility in terms of its, you can say it's the practical, you can say practical way of tackling the placement problem. Because in placement problem, it purely depends on mathematics. It tries to optimize a function. It sets a 0, it tries to find out x and y values, but it does not check whether there is an overlap in the process, right. And means when you are talking about the constructive placement, you can also have some heuristic. You can start with the block which in the default case will be having the maximum force. That will be the first block you select to move to the zero force target. In this way you can iterate. So either you can start with an empty scratch, or you can start with all the blocks in place, take them one at a time. So it is a number of ways you can handle it. Okay, so a number of other methods are there. I am very briefly talking about it. I am not going into the detail of these methods. See, Brewer's algorithm is interesting in the sense that it combines partitioning with placement. So here partitioning and placement are going hand in hand. The idea is very simple. I have a netlist, I have my floor plan. I cut the netlist, I also cut the floor plan. So, a part of the netlist will go here, other part will go here. I repeat the process. I cut the netlist, I cut the floor plan. I cut the netlist, I cut the floor plan. Finally, means each piece of my netlist will become small enough, and each portion of my floor plan will also become small enough. So a piece I can put into that small part of the floor plan. This is some kind of a divide and conquer approach. Okay. So, Brewer's algorithm is essentially this. This circuit is repeatedly partitioned, and at each level of partitioning, the available layout area is also partitioned. Now, how they are partitioned, a number of different ways of slicing have been proposed. I will show them. And each of the subcircuits which are obtained is assigned to a subsection. This repeats until each subcircuit is small enough, maybe a single gate or a few gates, which can be directly placed. This method is good, but in general it will not lead to very good placement, because you are basically cutting it with respect to certain criteria, but the final solution you will be getting in the process may be one where the net length may be pretty long. You are not putting enough emphasis on the interconnection, you are putting more emphasis on the gates or the basic components. The interconnections you are not putting much emphasis on. By doing this partitioning and placing them individually, maybe the interconnection wire length will become very long.
But actually the problem of placement, this interconnection problem is only
Yeah, but here interconnection is not being taken care of. Partitioning the graph, you are assigning them. But of course, while partitioning, you are trying to partition in such a way that the cut size is minimized, but still during the process of further partitioning, the two blocks may be going further apart, which were initially strongly connected. Okay. This will produce a correct solution, of course.
In fact, this can be used as a input for simulated algorithm.
Yes, yes, yes. There are a number of methods which give you a very rough and a gross solution, which is not very good, but okay, it is acceptable. That can be the starting point for the iterative refinement methods. Yes. So, this Brewer's algorithm defines 4 different types of cuts: cut oriented, min cut, quadrature, bisection and slice bisection. So, I am showing you what these cuts mean. But in the first kind of a cut, the sequence of cuts are like this. This is the layout floor area. Well, here you are assuming that the partitioning algorithm you choose, it is not a bisection algorithm. It does not divide a netlist into 2 balanced partitions. It will be unbalanced. The size of the partition will be 1:k, for example. So, you first make a slice like this. One part will be small, one part will be bigger. You do this repeatedly, then you slice like this. One part will be very small, the other parts will be bigger. Then 3, then 4, then 5, then 6, and this way you go on. This is called cut oriented. This is one method. The second method is quadrature. Quadrature says that in each step you divide the square into 4 smaller squares. The first step you divide like this. On the second step you divide each of them into 4. So, here the subcircuit at each step is divided up into 4 equal pieces. Well, this you can use Kernighan-Lin for the purpose. Just apply it twice, one after the other. First divide into 2, then 2 into further 2 and 2. Okay. So, quadrature placement can be applied for general cell arrays, like you can say for custom cell designs. You have the layout space where anything can be placed anywhere. You go on partitioning and going on placing. but there are some partitioning technique which are targeted more towards standard cell based designs. Like you see in the method of bisection, they do like this. First you cut like this, then you cut like this, then you cut each of these into half. First you slice using horizontal lines. This you continue until each horizontal slice is sufficient to hold one row of the standard cell. First you do this, and if you also do the partitioning of the original net at the same time, you know that which subcircuit you will have to put in which standard cell row. Then you try to map the corresponding netlist using technology mapping from cells of the library. Then you do vertical mappings, vertical cuts, and place them along the rows in suitable points. Similarly, in slice bisection is similar. You cut it like this, not using half and half. From one side you go on cutting. This each row width or height is sufficient for one row of standard cell. Then on the other side you do bisection. First you define what will go in each row of the standard cell, but while placing that you do bisection, 5, then half, then half. So, I have given you just a rough idea, but actually Brewer's algorithm is more complex than this. So, actually this involves a number of other heuristics also. But Brewer's algorithm works fairly well for standard cell placement because it uses this kind of a partition, but it assumes that you do not have any floor planning to start with. You start with partitioning and placement both together. This is a technique where partitioning and placement can go hand in hand. Okay. All right. And another approach, this is called terminal propagation. This is also I am mentioning very briefly. See, algorithms like Brewer's algorithm, if we apply it blindly, I told you, sometimes net length may be increasing. Why? Just I have an example in Excel, I am showing this. Suppose this was a scenario. There was a block A, a block B, which were interconnected. Suppose after a sequence of cuts, suppose the initial cut was like this, they are separated two parts, then again further cuts were made. So, it is possible that after a sequence of cuts, this module A will come here and module B will go there, which means that the length of this net will may become longer. So, there is no guarantee that two blocks which were connected together, they will still remain close enough. They may go to two extreme corners and the length of the wire connecting them may become very long, and if this is one of the critical paths, you are in trouble, right. Okay. So, to avoid this kind of a problem, well, a heuristic like called terminal propagation is used. Terminal propagation says that whenever a net connecting two terminals is cut, you introduce a dummy terminal. Now, see, this it is up to you. Do you apply this technique for all net cuts or only for critical nets? Typically, this is used only for critical nets. The concept of dummy terminal is something like this. See, whenever you cut this, you introduce a dummy terminal out here on the boundary of the cut. This is the dummy terminal. Okay. Now when this dummy terminal is generated, the partitioning algorithm will not assign the two terminals into different partitions. It will try to keep them in the same partition as far as possible. Well, I am giving an example here. Suppose this was the scenario that when this partition was generated, this dummy terminal was created. Now, after this partition, these two halves will be moving away from each other. Now, if they move away from each other, these terminals, well, a copy of the terminal on each boundary will also start moving away from each other. Now, these two are dummy terminals, these is kept separately track of. So, if you keep track of these dummy terminals separately, you will not allow these terminals to move apart greater than some specified distance delta d. This will be an additional constraint which you impose, that these dummy terminals will always remain close together. So, you will not allow these blocks A and B to be placed anywhere you wish. There will be some additional constraint you are imposing. So, using this terminal propagation, people have
But sir, now
tried
the
to solve
value
this problem.
between A and that dummy terminal can change.
So, this A and this dummy terminal will always belong to the same partition. This was actually what was said. Not assign the two terminals in a different partition. This A and this dummy terminal and this B and this dummy terminal, these two as a pair will always remain in the same partition for all future partitioning. So, you cannot partition it like this or like this. This is again just a heuristic which has been used to tackle the critical nets, nothing else. Just you are using partitioning, but instead of unconstrained partitioning, you are putting some additional constraint. You cannot cut this, or even if you cut this, you cannot move this away. Some constraint like this. Well, finally, a very simple algorithm which is used more as the initial point of iterative placement algorithm. This is called cluster growth. This is a very simple algorithm, where starting from an empty layout, you place the blocks sequentially based on certain criteria. The first block, which is called the seed, is usually placed or chosen by the user, and other blocks will be placed by the algorithm one by one, and the criteria of selecting the other blocks is usually based on connectivity with the already placed blocks. So, you have a layout, you first put one block, this is the seed, then you select a block which is most closely connected to this, most strongly connected to this, place it. Then take another block which is strongly connected to this pair, place it. So, this way you go on, but there is no provision of moving a block around in the placement, you go on sequentially placing it. Now, obviously, since we are not improving iteratively on the solution, layouts produced are usually not good. So, interconnections you are not taking into account, only the weights of connections you are taking into account. So, this is useful for generating initial placements only. Some of the blocks which are strongly connected, possibly you have placed them side by side, that is all, nothing else. So, the algorithm will look like this. B is a set of blocks to be placed. You select one block S from B and place it in the layout, remove that block S from B. So, while B is non-null, repeat, select a block X from B. The selection will be based on that weight I told you. Place X in the layout in a suitable place, take it out from B and iterate, simple. Oh, okay. So, summarize the algorithms that we have seen so far. Well, this cluster growth and a version of the force directed method, this can be used to generate an initial partition starting from an empty layout. You can systematically grow the placement to get a tentative, you can say, final placement. There are the simulated annealing and simulated evaluation and algorithms we have seen, which depending on probabilistic search techniques improve upon a given solution or a set of solutions, and we have seen that those algorithms typically give very good results for placement. And finally, we have seen some other methods based on partitioning, Brewer's algorithm and the terminal propagation, that heuristic. Now, there are actually many work which have been reported also, which can be broadly categorized into something called performance driven placement. Well, we are not only worried about the area, we are not only worried about the total interconnection length, but also the overall performance. So, here we are giving more emphasis on interconnecting wires and their lengths, in particular the critical nets. See, this performance driven placement has become important in the modern day scenario because today in a VLSI chip, the size of the basic components, the gates or modules, whatever you call, they are reducing in size, their speed is also increasing. Now, in comparison, the interconnecting lines which have also become very narrow and they are very closely spaced together, there are some other parasitic delays which are coming into the picture. So, finally, it will be the interconnections which will be dictating the final speed of the chip, like how fast the chip will work on. So, interconnection delay, this has become a major issue. If you want to make a circuit which will be running as fast as you want to running.
Sir, heat generated we did not take into account.
Heat generated we did not take into account, that is of course an issue. See, normally what happens is that many placement tools like you can look at some of the tools which are available commercially. So, while doing a placement it will not take care of the heat, but there is a tool using which you can observe a heat profile of the total floor area. You will find that some portion of the chip will get more heated than the other. Then through manual intervention you can modify the placement. This is a semi-automated process. Of course, there are some tools which have come up now which also try to do it in an automated way, but most of the existing tools will handle the heat problem in a semi-automated way. Well, if you find that some part are becoming red means hotter than the other, you may have to take out some blocks from some place it somewhere else, change some placement and again go back and iterate. See, this placement and routing, this will consume most of your, you can say, design time in the total VLSI design process, because you might have got the net list, but after placing you will find that a number of problems are coming in. You are not meeting the performance requirements, the heat problem is coming up. So, in order to tackle this you may have to go back, make some changes, again come down, again go back, again come down, this will have to iterate. Most of the tools will not be able to handle this automatically. Okay. Fine. So, the placement algorithms for high performance chips will allow routing to carry out within some specified. Now, these algorithms are still not very well established, some method have been proposed. Broadly, there are two major categories of such algorithms. One is based on the individual nets. Here you take one net at a time. Net means you take a net Ni which connects a set of points, and with respect to this net you see that whether the timing constraint are met. See, the idea is like this: the user have specified some kind of an overall timing requirement or constraint. Okay? There is a tool which will take the user level constraint as input and will try to generate net level constraint as the output. That means, in order to meet this performance requirement, I have to limit the total delay of this net to this much. These are, or range of delays should be between this and this. These kind of constraints are generated, and then for each of the individual nets the tool will try to place it or try to meet the timing constraint to 2 means within those ranges. Okay. So, the net based approach, the individual nets are taken and attempt is made to route the nets so that those constraints are met. So, the timing requirements, as I said, these are decided by the algorithm given the user constraint, and the tool I was talking about, this is called a pre-timing analysis tool. This pre-timing analysis tool will give you the bounds of the net delays. Well, net delays will finally get translated into net lengths, because lengths and delays are proportional. Okay. So, this is broadly one approach where the pre-timing analysis tool will give you a bound of the net lengths and you try to meet the net lengths.
So this timing constraint is given by the user.
Timing constraint is given by the user. I want to run my circuit at 100 megahertz, for example.
So these two algorithms are also algorithms for placement.
See, this kind of an algorithm, this cannot be a placement algorithm individually. So, here placement and routing should go hand in hand. Here just giving an estimate using semi perimeter method or anything, that will not tell you exactly what is the real delay. You will have to find out the exact routing path and see that whether the timing constraints are really met. So, for performance driven thing, placement and routing must also go on together. And the other approach is the path based approach, where you again analyze the circuit and you try to identify the critical paths and you concentrate only on the critical paths, try to optimize them as far as possible. These are two broad approaches. Of course, net based approach is more general in the sense that it can meet the user constraints in a much better way, but critical paths, as I said, that paths which are critical in one scenario, after some modification they may not remain critical, some other path may become critical, because as you move blocks around, the length of the interconnection paths may also go on changing. Okay. So, these algorithms, as I said, these are not independent algorithms, they must go hand in hand
With the placement.
with routing, because when you are saying critical path, when you are saying the net length, you must have an exact estimate of that, not a rough estimate. Because by the rough estimate you may say now that, well, I am meeting the constraint, but later on after routing you will see that you are failing to meet the constraint. Okay. So, continuing from here, in our next class we shall be moving on to the next step in the physical design automation, namely routing. We will be looking at the different sub problems of routing, and we will be trying to see that what are the different algorithms people use and what are the issues and challenges out there. Thank you.